Now we are ready to design slabs based on all the information we gathered so far. We gathered the information for moment, which is divided by into the column strips. This is column strips and this is middle strips. So we have a column strips here and middle strips on each at both ends of the column strip, which is right here, which is right here. So this middle strip belongs to this column strip, and this middle strip belongs to this column strip. Okay, so let's take a look at, well, this is column strip, and the middle strips that belongs to this column strips is this one and this one. What about this one? Again, this one belongs to this, right? And this middle strip belongs to this. So the middle strips is separated. One goes this, one goes this, right? So this is how the middle strips forms with the column strips. And we'll take a look at how to design. Before we do that, we have slab, something like this, and we'll take a look at just half of each is symmetric right here. Okay, so we are designing this part of the slab and use for the other part of the slabs right here. Okay, and then slab goes infinite this way, downwards, right? So that we're gonna design slabs for simplicity. The A1 B1 strip, which is edge strip, and A2 B2 strips, which is middle strips. But A3 B3 strips are repeating. So they are designs which is identical to A2 B2 strip, right? So we don't design A3 B3 strips, we don't design A4 B4 strip because they are same as the strip which is along with A2 B2 strip. Do you understand? Right? So we'll design this strip including middle strips and this edge strip including this middle strips. That's clear. Then we're going to start designing. And if you recall the column strip moment and the middle strip moment, we have a column strip moment here. So we're going to take a look at the A2 strip, B2 strip first, because they are symmetric. They're simpler. And then we're going to go and design edge strip as well. This is a moments which were divided into the column strip and middle strips. The middle strips are represented by the blue color, whereas the column strips are represented by the red color. And we have all the moment should be taken by the column strips right here at the edge when you don't have a edge beams, whereas we have divided the moment 60% and 40% for column strip and the middle strip respectively. And here the interior edge, we have a 92.3, which is 75% of total statical moment, and 30.8, which is 25% of total statical moment. And this is a moment that we need to design against at minus moment at interior span. If you remember, we had two moments, right? One from the interior moment from this span, and one interior moment from this span, and they were different due to the loading conditions and span lengths. As you see, there are different span lengths. But for design purpose, we follow the biggest moment. It's what we saw from last lecture, right? So those who are not familiar with the last lecture, you should go back and study before you listen and understanding this video lecture today. We have a minus 42.3. Okay, let me just take a look at this one. This is a real clear screen. Okay, minus 42.3 at exterior edge of exterior span is entirely taken by the column strip because we don't have any edge beam, if you remember. So that there's nothing to be shared by the middle strip here. This is middle strip. This is middle strip. These two middle strips belongs to this column strip. So this belongs to this column strip, and this belongs to this column strip. Now you clear how you share your column moment with? So this column moment is shared by this middle strip and this middle strip. And later, this column strip, this is second strip and third strip, this column strip is shared by this and this, right? So if you take a look at from here, this continuous type of diagrams. If you see second strip, this column strip is shared by this middle strip here, and this column strip is shared by this, right? So here I just made a little sketch to understand easily. I mean, nothing to understand, very easy, right? You understand what I'm saying? This column strip now is shared by this and this. Okay, so can I erase it? Okay. All right. So here, originally, we have a minus 42.3 moment, and there's nothing to be shared by the middle strip at corner. I mean the exterior span, exterior edge, right? So this is exterior edge of exterior span. Okay, exterior edge is a minus moment, right? Okay. Okay, this is minus moment. So this is nothing there, 0, 0, right? And use the red pencil, 0 and 0, right there. If you remember, here, all the moment is taken by the column strip at edge of exterior spans. Now when you go the positive moment, you share 60-40 between column strip and middle strip. That's what we know. So here, if you go into here, the magnitude, entire magnitude of the total statical moment is 84.7. Okay, I'm going very slowly because this is first time. It'll make you understand thoroughly. Here, this is the total statical moment is 84.6, and which will be divided by into 50.8 and 33.8 right there. Okay, so here this 84 is divided by 50.8 for column strip, and then here again I said actually the middle strip was 33.8, right? the middle strip. If you remember here, see the 50.8 and 33.8, but that 33.8 should be divided by 2. Should be divided by 2 here. Why? Because you have one middle strip here and another middle strip over there. You have two middle strips for one column strip, right? So we have two middle strips for one column strips. Okay. So we have to divide 33.8 by 2. So we will have a 16.9 taken by this middle strip and another 16.9 by taking the other side of the middle strip. Okay. And next is a negative moment. We decide to take a big one, right? If you remember, we decide to take a big one. Right here, big one. Okay. So let me just be patient to show you one more time. See here, we had a two moment here. Then we decide to take the bigger one right there, this one, which is minus 123.1 at the negative moment. That is divided into 75% and 25% for column strip and middle strip, if you see over there. Okay. So this goes minus 92.3, and also the middle strip should be divided by 2 to be sure the column strip located in both ends of the column strip. So this is 15 minus 15.4. This is minus 15.4. Okay. And there's another positive moment. Okay. And this positive moment is going to be divided by 39.8 and 26 something, which is divided by 2, becoming 13.3 at this middle strip and this middle strip. Alright. So now do you understand how we separate them into the column strip and middle strips? Right there. Very easy to follow, nothing confusing. So I'm going very slowly, patiently, so you can follow me easily. So this is very important. This is, I had a two difficult part that to teach in slab design. This is one of them, but obviously this is not difficult if you carefully follow my instructions. Right? So, right, and we do A2 strip to A3 strip in a similar way. If you see here, we do A2 strip, we just did A2 strip, and we can do A3 strip and A4 strip, and we're gonna go and do it infinitely because this leg repeats infinitely downwards, right? So the A2, A3, A4 strip right here, now all done because they are all same. Understand? Okay, now the different strip, of course, this is A1 and a B1 right here. So we're gonna magnify it and take a look at this. So let me just erase this one to see this part more clearly. Okay, now we have a minus 23.5. You want to take a look at one more time? See here, we have a minus 23.5, and the inside minus moment we have two. One from this span, one from this span. So as long as they are different, we have two different negative moment, which is minus 63.4 and minus 68.4. And this is big moment in negative region. So we'll take this to design the slabs. And same here, this one. Easy. Okay. And here we also have a moment induced by the walls. This is wall loading. Minus 5.3, and we have 2 wall loadings, but we're going to take a bigger one at joint. I'm going to take a bigger one at this joint. Okay, this is the loading moment demand induced by the wall loading. Okay, and we're going to take a look at these two, one from slab loading and one from wall loading at A1, B1, C1, D1 strip. We'll take a look at the one part of the symmetric because they are both symmetric and they share the same design. Okay, as just we see over there, minus 5.3, and this is wall loading, and this wall loading should be supported by the column strip because there's nothing out there, right? This is wall. You have a wall here. You have a wall over here. You have a wall over here. Do you understand? Do you have a wall over here? Okay. So you can say here, if you look at this way, we have a wall here. We have a wall over here. This is wall. Wall induce a wall induced moment. Okay, wall induced moment. Alright, so this is wall. This is wall loading. Wall, and we have a moment. See, and these are the wall loadings. These are the wall loadings. We just saw it, right? We just saw it. Okay. Alright, so but the wall loading should be resisted by the column strip. The wall loading should be supported. Okay. So the wall loading, okay, wall loading should be supported by column strip. Okay, so this wall loading, all wall loading goes into column strip, right? Goes into column strip. This is edit, right? And this is edit into the column strip moment. Do you understand? Okay. And the moment from column strip was divided into the column strip and middle strip. So we don't have middle strip over there. We only have one middle strip. We have here again one middle strip, for edge strip. Okay, one middle strip for edge strip. We have a two middle strips for interior strips, right? But we have one middle strips for edge strips. So all this moment divide into column strip. So one column strips and one middle strips. But at the corner, we don't share the moment with middle strips when you don't have any edge beam. So I'm repeating so many times. Okay. And next moment in positive zone is 47. And how we decided to share? See, 47, we decided to share 60% and 40% for column strip and middle strip respectively here, if you recall. So this 47.1 and the 60% of that is 28.3 is going to be shared by the column strip right here, and which is 40%, 0.4 right there, which is 18.8 is shared by the middle strip, but entire 18.8 should go here because we have a one middle strip for edge strip. So now you understand the entire numbers in this plots, right? So they should be understood in order for you to make a correct slab designs. And next one here, minus 68.4 is taken by 75%, and 25%, which is minus 51.3 and minus 17.1 by one middle strip for edge strip, exterior strips. And the positive one, next one is positive, and go in 60-40. You can do the same thing here. 60 is 22.1 and 40% represents a 14.7, right? Okay, now we do for both the interior strips and exterior strips. Everything is clear, right? So let me just erase to get more rooms for writing again here. Okay, hope you understand what I'm erasing right now. Take a look at here. The moment now should be summed up, should be added up, so that we have, take a look at this middle strip is one middle strip. We're going to design this as a one beams, okay, later. So that we want to add all the numbers that was recorded on this middle strips, even if the number came from different column strips, right? So this number was coming from this column strip, and this number came from this column strip. Once they are in this middle strip, they are now family. They are added, and there's nothing added for exterior span of exterior moment. And we have this moment from this column strip and this moment from this column strip, but they are now family. They add and add, so on and so forth. Okay, so that the design moment here As a matter of fact, is this 37.6 for positive and 0 for negative at exterior edge of exterior span, and we have interior span, we have a minus 32.5 and another positive 28, and this repeats for the other side of the slab, because this slab and these slabs are symmetric. Right now, same thing here. Okay, so we will design one part of the slab only because the other part of the slab is identical from a center line because they are both symmetric. Alright, so we have a slab loadings all down here. So what's slab loading? This, and for middle strip, and we have slab loading for column strip. This, right? And this number is not right. Okay, this number should be 92.3. Okay, so let me just fix it here. Say this one minus 92.3, this one minus 92.3. That should be same as this number. They're all same, right? Okay, this. So we have all moments. So now we are ready to design. Okay, let me just fix this. Minus 92.3 minus 92.3. So we have all moment here. We can design, right? So this moment is designed based on the width of this middle strip, and this moment and this moment, all this moment on column strip is based on the width of this column strip, right? So what you can do is that you design the rebar for these moments and divide it that by the width of the middle strip. Okay, and the width of the middle strip. Okay, and designs are easy. We learned from RC1. We designed this based on beam theory. Alright. Based on beam theory. What's the beam theory? Moment is AS Fy D minus A over 2. This is beam theory. Right? So we know the we assume depths of the slabs, which is depths of the beam, and you can calculate the depth of the compressive concrete block. A is the depth of concrete block. Now we know the Fy, so we can calculate AS is a rebar area. Okay, so the AS is a rebar area. So I cannot go through all these designs, but you have to do yourself on your own using your RC1 theory. So let me just take a look at one little example only. If you want to design minus 92.3 and the particular slabs right here, which is a column strips, and you can use this simplified equation for beams. Here, where mu is a factored moment, so you're going to use a 92.3 right there. You can assume D, or D was assumed the 180 millimeter, and we subtract the cover and half a bar diameter. This is the effective depth. So we saw that before. I'm not going to repeat right here. D. So D was assumed the 152 right here. And then phi factor, the strength reduction factor, we have studied that at 0.9 for fractional member, and Fi was assumed to 300 megapascal, and D is 0.925 times 152. All these numbers are identifiable from RC1 knowledge. Nothing is very difficult. So you need to go back to RC1 and study for design. The RC1 is everywhere. So that you need to keep that information in your mind to design for all other materials like columns and slabs and walls and foundations, right? Okay, now this is the depth of the concrete compressive block here, and this is a Whitney coefficients. Okay, and this is the width. Width is this thing which is different from beam design. Only thing that is different from beam design in this chapter, Wight 20-50. See, both beam strip and column strip, the width of the strip, slab strip, is 2250 millimeter for both middle strip and column strip, as you see over there. So this is B. So you can just use this B in your equations when you calculate rebar area. So we have a B over here, and A was 12.7 millimeter, and we use a phase 0.9 when it is in tension controlled limit. So you have to review this from RC1. When we are in tension controlled limit, we can use 0.9 for phi factor, and I'll give you one hint. See, the strain level and the rebar is greater than 0.005 for tension controlled limit, right? The rebar strain is greater than 0.005 for tension controlled limits. So this is what we see here. The effective depth was 152, the top of the section to the center of the rebars. This is a east-west direction. We calculate right there. So we use this D and this formula right here. Okay, this formula right here, and this, we got the rebar area very quickly. And then we have to check the section is controlled by tension, and then we can use fecal 0.9. Alternatively, we may check this way. We can calculate strain based on strain compatibility. We see this from column section, how to calculate strain based on strain compatibility, right? So we calculate strain at rebar is 0.0276, which exceeds 0.005. As I said, the slab is tension controlled region. You can use phi as 0.90. This is greater the better, right? We can have a economic section when you have a tension controlled sections. When you have a rebar strain which is greater than 0.005, and the strains can be calculated based on the strain compatibility right there. And these are all things that we learned in RC1, and I have repeated in column section. So you can go back to column section and how to see how to calculate the rebar strain based on strain compatibility. And also I have given you a lecture on how to calculate the phi factor based on the ductilities, which is function of the strains of rebars. Okay. So we calculate here all the necessary information to calculate the compressive concrete depth, and this is a review, but you know, I'm just trying to do one more time to refresh you, but you should be able to review yourself for the other examples here. Okay, we got all this calculate very easy, and we calculate also this one, JD, right? This D minus A over 2, which is this, and A was 12.7. This is simply calculated the depth of the concrete block. Here is it, very easy, right? Nothing so difficult. So now we are ready to go and calculate the rebar area. Okay, so if you see here, I summarized for here during the break, and the mu is phi times ASFI T minus A over 2. This is very famous formula from concrete beams, and you want to calculate the rebar area. This is design, so that this is given. This is 92.3 times 10 to the 6, and phi was assumed to be calculated to be not assumed, calculated to be 0.9 because they are in tension control, and 300, and this value was 145.7 from a few seconds ago, and we get this value, right? So this value is amount of rebar which is equivalent to 12 rebars of 16 millimeter diameter rebars, right? 12 16 millimeter diameter rebar, and they are indicating design document is in figure 13, 69 and 82, 83. Let's take a look at that. So this is a schematic design of reinforcement in east to west strip that we just finished calculating, and we are looking at A2, A3 strips where we found and used it for calculations, which was 92.3, and this is the rebars, right? We have this rebar, right, passing through the top of the slab, right? Okay, now do you understand? Okay, and we designed this rebar. Okay, we designed this rebar. So the rebar, you can calculate all the other rebars. See, we have a rebars at H column strip. We'll calculate rebar here, rebar here, rebar here, rebar here, and so on and so forth. We just calculate rebars here right now. This one, okay. And this is what you see over here. This is what you see over here. This is column strip, and this is mid strip for H, I guess, and this is a column strip, and this is mid strip, and we repeat this way all the way, right? So this each column strip and mid strips are obtained in terms of the number of rebars in this way. Okay, and you saw how to calculate that one by one. Okay, the ACI requires a minimum rebar area for slabs. See the ACI section 13.3.1 section 13-9. The Korean code has a similar requirements, and this section says slab minimum rebar area is 0.002 pH for grade 300 reinforcement. And after you design this rebar we just saw a few minutes ago, and we have to check the minimum slab rebar area, and this AS equal 0.002 pH for FY 300 megapascal, and we need to calculate B. So what's B? Let's take a look at the H slab right here. So can I erase some? Get a clear view here. Okay. Now we understand everything. Yeah? So if you see over there, and this is width for H slab, and here we have a slabs, original slabs from here to here, and we have here 100 millimeter for walls. Okay, it's hard to draw because this is small, right? from here to here. From here to this is a wall. So 100 millimeter. And also we have a half of columns from here to here. Right? You got it? So we have here half of column with this. It's very difficult. Okay, let me do this way here. So this is end of slab edge, and we have a column. The mid section we have this is 100 given for wall installation, and here this is a column B divided by 2. So column is 300, B is 300, so this is 150. So this length here, width here, 250 millimeter. Right? So that if you go back to this equation right here, see, you add this is 45. Okay, and then we have to subtract this and this from 4,500, right? In order to get the width of the edge slab. So my equation should go 4,500 minus this and minus this. This is half of this, right? So my equation goes like 4,500 minus 2250 minus half of 2250. Half of 2250 is this, and we have to now add this, which is 250, right? Because we have another edge strip extended from the edge of the original slabs, like that, for walls and half B of the columns. Okay, so we have this which should be added, right? So this entire width of the beam is 1375. So we go here 1375 times, which is H is 180. So here 180. So we need a minimum slab rebar area, 495 millimeter square. Okay. So the reason I went through all these calculations is detail. Okay, so good engineer with good detail. This is what all the engineer knows about, right? So that if you want to be a good engineer, you want to be a good detailer. You're going to take a look at these numbers without making mistakes. So I'm not going to repeat from next examples, but I just went through to help your understanding how you detail the width of the slab. Okay, so again, you from 4,500 you subtract this, and you add this. Right? This is add. I'm very patient to explaining this. Okay? This is good detailing. Okay, so we take a look at the final conclusions of the slab design for this strip. We have a 495 millimeter. You can take a look at these little lines over there. You may understand, but you'll understand much easier with my explanations. Won't you? And this, and also the ACI says your maximum spacing is 2H, 2 times the height of the slab, which is your having a 360 because your edge is 180. Okay, and even though your spacing cannot be farther than 500 millimeter. And this all, I told you, good engineer with good detail. This is the law, regulation, requirements, and the more you memorize them, the more efficient engineer you will become. And people will recognize you with your good details. Alright? So that your minimum rebar, if you are assuming that your maximum spacing, if you're using maximum spacing 116 millimeter, and this is the width of the slab, you need at least 4 in order to meet the maximum rebar spacing on the slabs like this. Okay, so let's take a look if you have a minimum rebars more than 4 or not. See, this is a, if you use a 16 diameter rebars, then you may only need a less than 3 rebars to satisfy the minimum slab rebar requirements. So that, because the diameter for 16 millimeter diameter will give you the area of 200, around 200. So the area, rebar area for 16 millimeter diameter will be about 200. So that this is about little less than 3 16 millimeter diameter, but you need a 4 for minimum, because you need a minimum number of rebars of bar spaces is determined by the maximum rebar spacing, which is 360, right? So you can go further 360 for the 1375 with slabs. You need at least 4. But when you calculate the rebar area by the minimum rebar ratio formula, you need 3. Right? So you should stick to these options, right? Which is 4. So the rebar, number of rebar for minimum is 4. So even if you calculate the rebars that you need for emitting a moment for strips, you have to check the minimum rebar ratio. See? So minimum rebar ratio can be checked based on 2 things. One is based on the maximum rebar spaces right there, and also based on the formula that's given in ACI. But in any cases, your rebar that you calculate based on the moment is a lot greater than this. So how many? We need a 12 rebars, right? So 12 rebars is significantly greater than 4, which is requiring based on the maximum rebar space. Okay. 제가 끝에 와서 굉장히 자세하게 지금 설명을 했죠, 그죠? 끝에 와서 제가 디테일을 전부 다 설명을 했습니다. 여기 책에 나온 디테일을요. 그래서 여러분들이 이제 잘 이해가 가실 거고, 이 교과서를 읽어보셔도 이제 이해가 다 잘 가실 겁니다. 그죠? 그래서 이제 마지막으로 이 도면을 그리면 설계가 끝나는 거죠. 자, 우리가 지금 이제 이스트 웨스트 스트립만 하나 했는데, 다음 시간에 우리가 노스 사우스 스트립도 마저 하고요. 여기 있죠? 노스 사우스 스트립 설계 마저 하고요. 그리고 다음 시간에는 이제 이 부분은 설명을 안 하겠습니다. 이번 시간에 아주 자세하게 설명을 했어요. 그렇죠? 다음 시간에 이 부분은 이제 이거 다 하다가 뭐 진도 못 나가지요. 자, 그래서 아까도 얘기했지만 슬래브에 있어서 굉장히 중요한 2가지 중에 한 가지를 오늘 했고요. 물론 이제 다음 시간에 노스, 사우스 같은 종류지만은 이제 하나가 더 남았는데요. 그것도 이제 마저 다음 주에 끝내도록, 이번 주에 끝내도록 하겠습니다. 그리고 첫 시간에 우리가 알파를 배우면 돌아오겠다 한 내용이 있죠. 이제 그 내용으로 돌아가서 Direct Design Method에서 필요한 우리가 7가지 assumption을 이제 마치겠습니다. 여기 보면요. For panel with the beams between supports on all sides, the relative stiffness of the beam is in two perpendicular directions given by alpha 1 L2 square over alpha 2 L1 square shall be less than 0.2 or greater than 5. Term alpha as defined in next section, and L1, L2 are the spans of the two directions. 자, 여기 보세요. 이제 알파는 우리가 뭔지 알죠, 그죠? 빔에 대한 슬라브의 스티프니스를 이제 비교한 거죠. 어디 나오죠? 잠깐만 기다려 보세요. 다시 한번 제가 확인해 드리겠습니다. 여기 나오죠, 그죠? 빔에 대한 슬라브 스티프니스에 대한 비교죠. 이 알파입니다. 자, 빔이 없으면 뭐 알파는 이제 제로가 되는 거죠. 그때 이제 이게 한 방향의 그 스티프니스에 대한 비율 대 그 직각 방향으로 있는 비율이에요. 그래서 L1하고 L2는 직각 방향이죠. L1하고 L2는 직각 방향의 빔이에요. 그래서 한 방향의 그 빔이 얼마나 강하게 들어가 있느냐 하고 또 다른 방향에 또 빔이 얼마나 강하게 들어가 있느냐 이런 뜻이죠. 이 의미 아시겠죠? L2 방향에 빔이 얼마나 강하게 들어가 있느냐. 그럼 직각 방향인 L1 방향에는 빔이 또 얼마나 강하게 들어가 있는가. 이 알파는 빔의 슬라브에 대한 강성비라고 그랬어요. 그죠? 바로 전에 봤죠? 이 비율이 한쪽으로 기울지 말라 하는 뜻입니다. 그렇죠? X, Y 방향 두 방향으로 빔이 너무 한쪽으로만 많이 넣지 말아달라는 얘기죠. 왜? Direct Design Method를 이용을 하기 위해서는요. 그죠? 그래서 그 비율이 얼마냐? 5배거든요. 5배 적던 간에 5배 많던 간에. 그렇죠? 5배 적던가 5배 많던. 그러니까 그 비율로 그 이내로 해달라는 얘기죠. 빔을 넣을 때는. 이해가시죠? 여기에 보시는 이 도면이 This is our conclusion for slab design today with the east to west direction, and the north-south direction explanation will be very short because we will apply the information that is identical to what we have learned today. So that won't take long time for understanding and designing and creating these construction documents for rebars with north-south directions. And then we're going into the design for slabs for unbalanced moment. It is very important part of the slab designs, and that's the way we're going to go in and finish slab design soon. Thank you.